Hello.
Yeah, good evening, sir.
Good evening,
Yeah,
sir.
good evening. Okay, so we'll be starting with number theory from today. So the first things here are how do you study the topic? You can use the following textbooks. There is Joseph Silverman's book on number theory. It's a brief introduction to number theory. It's a very good book. Then there is AOPS book by Matthew Crawford, which is Introduction to Number Theory. That's also good. Introduction to NT. And then the third book would be Justin Stevens. It's a handout, not very long, which is Olympiad Number Theory. Olympiad Number Theory. There are several other handouts like that. This is one of them. There is another one, which is Modern Olympiad Number Theory, which is called Mont, which is also a good book. So these are the books that you can use that I would say are good. Other than that, basic number theory is already covered on the channel. There is a lot of videos on number theory which are covering the basics that you need. So that you should use. The channel videos are already available. Lots of them are available. Plus, there's an introduction to number theory course on Udemy also, which you can use. So introduction to number theory course covers a little bit more than the introduction, but it has enough theory to get you started at least for the first couple of levels of your Olympiad. So I am making an advanced number theory course, but this is good enough to get you started on Udemy, other than the textbooks. Uh, Number theory is a super important topic. It is essential to Olympiad maths. You need to know it. It will have applications in higher maths also if you study maths in the future. It's one of the fields that there is a lot of research that is going on. So it is super important. It's also quite difficult. Like the reason it is difficult is because simple statements are often very hard to prove, and there are many of these simple statements in number theory which are difficult to prove, and you can make a conjecture, but to prove it is a different matter entirely. It is difficult. The proof methods that we use in number theory are typically induction. So if you don't know induction, you need to learn mathematical induction. If you have taken the Math Olympiad Masterclass course on Udemy, there are several videos on induction there. And there are different types of induction that I have discussed. So there is strong induction, weak induction. There are several other types of induction, spiral induction also that I have discussed there. So if you have taken this course, you should refer to the videos on induction and learn induction. So that is one of the proof methods. The other proof method is obviously contradiction. Typically, these are the two proof methods you will use, and we will be using them extensively in our discussions. So if you are not familiar with it, I would recommend that you find the resources and study those things. We will not be starting with the bare basics, very basics of number theory, because I'm assuming that all of you already are aware of the basics. So, like, we will start with divisibility and congruence. So you can call it typically a first chapter of number theory, but we are not going to start at a very low level. Like I'm assuming that you will do the homework, you will watch the videos or do the books enough to know your basic number theory so that you can approach our classes here with a little more confidence. So that's about it, the introduction. Now we'll start. Does anybody have any questions?
Like in which order to do the books that you mentioned?
There is no order in which you have to do all. You don't have to do all of them. You can pick any one book and do it properly. Matthew Crawford's AOPS book is the easiest. AOPS book is easy. You can start from there. Higher difficulty level would be slightly higher difficulty level is Joseph Silverman's book. Joseph Silverman's book is slightly higher level and it is also more comprehensive. This is probably the most comprehensive book. It has the most stuff. And it is also easy to read, so you should try that. Then you can look at MONT or Justin Stevens. These are slightly different. They don't teach you theory so much. They are about problem solving and they're about IMO problems, how to handle problems in number theory at higher levels of Olympiads. So they are slightly advanced. You should begin with either this or this. Or you can start with any of the courses that I have on YouTube or on Udemy. You can use those. Okay. We'll start off with the first problem.
Sir,
Hmm.
excuse me, sir. Will
Yeah.
we get assignments?
Yes, you will get
Okay.
assignments. Where are you asking? Assignments from where? For these classes?
Yes.
Yes, I will share the assignments, but first you have to learn some theory before you can do assignments. So
Okay.
the first problem is this. Let n be a positive integer. Show that if n integers are given, then there is a non-empty subset of these integers whose sum is divisible by n. I hope everyone understands the problem. Think about it.
Sir, the n integers are given from 1 to n or they are randomly n number of integers.
There are n integers randomly. Okay, I said it's from 1 to n.
Okay.
Let n be a positive number here, so that if n integers are given and there is a non-empty subset of these integers whose sum is divisible by n.
You should mute yourself.
Oh, sorry.
The hint is pigeonhole principle. Does everyone know what is pigeonhole principle?
No, sir.
No, sir.
Does anybody know?
Sir, when it's like when we have 7 holes
Hmm.
and 8 pigeons, then
Hmm.
at least one hole will have at least 2 pigeons.
Right. So when there are k holes and k plus 1 pigeons, then some hole here will have more than one pigeon. It seems very obvious and doesn't feel like it deserves a special name, but it has a lot of applications, and you will be surprised by the kind of problems that will be solved by just this. So we will see how we will solve this problem using pigeonhole principle. Think about it. You have n integers. We can call them a1, a2 till an, right? These are our n integers. Now, the question says there is a non-empty subset of these integers whose sum is divisible by n. That is what we have to show. So first of all, you would have to create those non-empty subsets, right?
Yes.
Yeah.
You will have to think of what are the possible subsets. So you can say subset 1 could be just a1, right? And actually, we don't care about the subsets. We care about the sum of the subsets, right?
Yes, sir.
We, if a subset is a1, a2, we care about a1 plus a2, right?
Yes.
So I am going to call, I cannot take an empty set as a subset. That is not allowed. So I have taken right now one element. Then I can take another like this. Then another subset whose sum could be these three, right? Similarly, there can be n subsets. There can be a subset where there is a1 plus a2 plus an, right? Correct.
Yes, sir.
Actually, there could be more subsets also, but our argument works even in that case.
Mm.
You can imagine that there can be more subsets. No, there could be a2 plus a3, a3 plus a4, and so on, right?
Yes, sir.
But our argument doesn't need more than this. We have shown that there has to be at least n subsets, right?
Yes, sir.
And each of these n subsets will have some sum, right? Correct.
Yes, sir.
Yes, sir.
We'll have a sum. No, the total number of subsets is actually 2 power n minus 1, the number of non-empty subsets, right?
Mm.
We are focusing only on these ones, the simple ones, where we are starting from a1, then a1 plus a2, then a1 plus a2 plus a3 till a1 plus a2 plus an, right?
Yes.
Now, think of what happens when we think about divisibility by n. Divisibility by n, इसके बारे में सोचना है ना? We have to prove that one of these sums is divisible by n, right?
Like it is like n into something.
हाँ, डिविजिबल बाय n का मतलब तो सबको पता ही है ना.
Yes,
We
sir.
have to prove that it is guaranteed that one of them is divisible by n. कोई भी इनमें से कोई एक, right?
Hmm.
Actually, number of subsets तो इससे भी बहुत ज्यादा है, but if you can show that इनमें से कोई एक है, तो same argument will work for more of them also. Okay?
Hmm.
Hmm.
So what you can say is whenever you divide a number by n, how many remainders are possible?
Till n minus 1.
N minus 1.
N minus 1.
Right. The remainders possible are 1, 2 till n minus 1, right?
Hmm.
1, 2
Yes,
till n minus 1. Correct?
Yes, sir.
If they are not automatically divisible by n, right? अगर
Yes, sir.
रिमाइंडर 0 होता तो डायरेक्टली डिविजिबल बाय n हो गया, राइट? Do you understand what I'm saying?
yes, sir.
So that case we don't have to worry about where the remainder is 0, because then that subset is the answer, right?
Hmm.
We
Yeah.
are worried about the case where none of them is divisible by 0, but then the remainders have to be in these boxes, right?
Yes,
Or
sir.
in these holes.
Hmm.
And these sums are the
Hmm.
pigeons.
Hmm.
Okay.
If the sums are
अच्छा.
the
Okay. So
pigeons,
we
Hmm.
have
there are
n pigeons and n minus 1 holes.
हाँ, तो one pigeon
remainders,
must be in.
right? So then that means that at least two of them must go to the same hole, right?
Yes, sir.
So two of
Hmm.
them, Si and Sj, must belong to the same remainder class, right?
Yes, sir.
These are called residue classes. Later we'll learn the name residue classes. Whenever you divide by an integer, the number of remainders possible are called different residue classes. So there are n minus 1 residue classes right now. So we are saying Si and Sj belong to the same residue class,
Hmm.
or they leave the same remainder when divided by n, right?
Hmm.
Is everyone understanding so far?
Yes, sir.
Yes, sir.
Everyone else?
Yes, sir.
Okay. So if Si and Sj have the same remainder, then when divided by n, so you can imagine they would be numbers of this form. Some kn plus some remainder and some
Okay.
ln plus some
Then we
remainder.
can subtract.
The remainder is same, so we can subtract and say that the subtraction is divisible by n, right?
And that is also gonna be
Yes,
like
sir.
part of some set.
So when you do subtraction of
Hmm.
Si and Sj, you will realize that if it is S2 and S4, then some elements will be left over in that subtraction, right?
Yes, sir.
And
Yes,
that
sir.
leftover stuff is also a subset of the original numbers.
हाँ.
So we have proved that the subtraction is divisible by n, right? And the
Hmm.
leftover elements, जो भी बचेगा, those elements, the sum of those elements is divisible by n.
Hmm.
So therefore, there is a non-empty subset of these integers whose sum is divisible by n.
Hmm.
Is it clear why it is working?
Yes, sir.
Yes, sir.
So that is an example of pigeonhole principle and how we are applying it. So what you have to decide in such problems is what is our pigeon and what is our hole. Here the set of sums of the subsets was
Hmm.
our pigeons, and the remainders when you divide them by n were our holes.
Yes, sir.
And then automatically it worked, and we got that the Si minus Sj will be divisible by n, which implies that at least some of the elements will add up to a number divisible by n. Right?
Yes, sir.
Okay. So that is one example. Now, the work that you have to do is prove two similar problems. Prove that among any three integers, there are two whose sum is even. And B, prove that among any 5 integers, there exist three whose sum is divisible by 3. These are strong statements. Think about how you can go ahead and prove it. These are very powerful statements. I mean, second one especially. First one seems like an obvious thing, but you have to prove it nevertheless. Even if it seems obvious, you need to show a good proof for it.
Then, oh,
Hmm? Both of these are actually special cases of a famous theorem. It has a name, Erdos.
the first one, I think, done.
Discuss it. Erdos-Ginsburg-Ziv theorem. And the proof of the theorem is much more difficult, but I will state the theorem. It says that among any 2n minus 1 integers, there exist n integers whose sum is divisible by n. You can see that both A and B fit it, right? We are not going to discuss this theorem's proof. We are going to do the special cases. So who has done first one?
Sir, we can take 4 cases for first one.
Mhm.
Either three, case one, like all 3 will be odd, or 2 odd, 1 even,
Mhm.
or 2 even, 1 odd, या
Mhm.
फिर all 3 even.
Okay. I mean, that's the right idea, but you don't have to do that much work because you are taking too much cases and all. All you need to consider are the even odd nature, right?
Yes,
If you
sir.
think of the even odd nature, these are the holes and these are the boxes, pigeons, three integers.
Okay.
If you put
Yes.
three integers in these two boxes, automatically it is guaranteed that it is at least
Either
one
one
of
will have
either one of
either
them will have
two even.
two,
Yes.
two or
So
more,
it
right?
will make the sum even. Like either two odd or either two even.
Right. So if it is two odd
Okay.
and one even, that also
Hmm.
works, right? Correct? And if it is two even, then
Yes. Yes.
automatically there are two whose sum is even, right?
Hmm.
Hmm.
Do you understand the two even case? You don't have to do anything,
Hmm.
right?
Yeah, first
Hmm.
one is
Yes, sir.
pretty easy. Like we can do cases and all.
हाँ.
But it is better to use PHP, pigeonhole principle,
Yes,
where
sir.
you
Cause
directly realize
like
it.
अगर थोड़ा सा बड़ा केस आ गया तो वहां पे ऐसे केसेस बनाना बहुत लेंदी हो जाएगा.
फर्स्ट वन को बिना पिजन होल प्रिंसिपल के भी कर सकते हैं. यू कैन से इट लाइक दिस. If A, B, C are three numbers, you should realize that A plus B plus A plus C plus B plus C is twice of A plus B plus C, right?
हाँ.
The right hand side is always even.
Yes, sir.
So these cannot all be odd.
Hmm.
All three cannot be odd, right?
Hmm.
If all three are odd, the right hand side cannot be even.
Even. Yes, sir.
If all three are not odd, one of them is even, which is
Hmm.
the proof.
Hmm.
So without pigeonhole principle also, if you notice this, you can say it is done.
Hmm.
But pigeonhole principle is also obvious. Prove the second one. That is not super obvious. It's the same idea though, so you should be able to do it.
Done, sir.
How? How is it done?
Pardon?
Whoever has done it has to share the proof.
Yes, sir, like we have 9 combination. How can we add 3 numbers? A1 plus, like, let A1, A2, A3, A4, A5 be and any 5 arbitrary integers. Then there are 9 possibilities like how we can add these 3 integers. So
Which three?
any 3.
5C3 is 9. There are 10 possibilities.
Oh yes, sir, 10. Sorry. एक भूल गया.
That's not the way to solve this question. How can you do it by 10 numbers, dude? What if I had put 15 on all them? You understand what I'm saying?
Yes.
That's not a way to prove the question. You cannot start listing all the possibilities one by one. You have to use pigeonhole principle or whatever method, but it has to be something better than this, right? You will not have a time in the exam to list all the possible options. And if the number was slightly bigger, you could not do that. You have to think of applying pigeonhole principle. You have to think of what are the possible remainders that come when you divide a number by 3. Remainders are 0, 1, and 2. How many numbers are there? There are 5 numbers
5.
for us. So, first of all, we'll do the case 1 where at least one number of each kind is present. At least one here, greater than equal to 1, greater than equal to 1, greater than equal to 1. It is possible, right? Do you understand what I'm saying right now? Out of the 5 numbers, all 3 types of numbers are there. What are the 3 types of numbers? Numbers which leave remainder 0, remainder 1, or remainder 2 when divided by 3. Numbers of the form 3k, 3k plus 1, and 3k plus 2. So there will be a possibility that all 3 types of numbers are present among the 5, right?
Yes, sir.
If all the 3 types of numbers are present, you should take one of each type. If you add them, what will happen?
3k 1 plus 3.
Divisible by 3.
3k1 plus k2 plus k3 plus 1.
That is clearly divisible by 3. If you
Yes.
add the numbers of all the 3 different types, you can select 3 numbers which will be adding up to a number divisible by 3. Right? So case 1 is already sorted. Case 1, there is no issue. We can find 3 numbers which are divisible by 3. Now we need to look at cases where one of these types of numbers is missing. Right? Let's say 0 type of number is missing. Only these are present. Right? Or any of them is missing. It doesn't matter.
Mhm.
Now there are only 2 types of numbers. How many numbers are there? 5. Right?
Yes, sir.
Yes, sir.
If there are 5 pigeons and 2 holes, how many at least there will be one hole in which there will be 3. You cannot put 2 and 2 now. You have to put a third one in one of them, right?
Yes.
As soon as you put 3 numbers in one box, what will happen? Those 3 numbers, if you add, it will be divisible by 3. Do you understand what I'm saying?
Yes, sir.
Suppose there are 3 numbers which are leaving remainder 1. Then can you see that when you add them, they will become divisible by 3?
Hmm.
Even if it was 2, 3k plus 2, then also it will be divisible by 3, right? Do you understand how we are eliminating so many options quickly?
Yes, sir.
Yes.
Case 1 was where all 3 types of numbers were possible. If that is true, we can take one number from each of those types. And that will give a number divisible by 3 when you add them. And next case is, okay, one residue class is missing. So you have 2 remainders and 5 numbers. By pigeonhole principle, at least 3 of the numbers have to have same remainder, right?
Yes, sir.
As soon as that happens, you take those 3 numbers, and those 3 numbers when you add will be divisible by 3. I hope it is clear what is happening.
Yes, sir.
Okay, so this is another technique, proof technique. So pigeonhole principle should be added to your proof techniques. I wanted to show this because maybe you guys were not aware of it. There are many questions based on this. You can find many handouts on this online. You should search and learn this particular topic. Basically, induction, contradiction, and now this special technique, which helps in proofs. Now we'll start off with the basic theory. And the first thing that we learn about is properties of divisibility. Divisibility properties. So first of all, divisibility follows the reflexive rule. Reflexive rule, which means A divides A for all A belonging to integers. So anything that follows this property, that there is a relation between an element and itself, that is known as a reflexive relation. So divisibility properties we are looking at. So first of all, it satisfies reflexive rule. Then it satisfies transitive rule, transitive property, which means that if A divides B
B divides A.
and B divides C, then A divides C, where A, B, C are all integers. By the way, we will be using a symbol for divides. We will be saying A divides B. This means A divides B. And if we say something like this, then we say A does not divide B. So remember this notation. This notation is pretty standard. So when I say A divides B, what it really means is B is equal to A times K, where K is some integer. Right? Do you understand what I'm saying? If A divides B, then B is a multiple of A, right? So B is equal to A times K. That is another way to say that A divides B. So the transitive property is true. You can easily prove it. I will not prove it. It is obvious. So basically you can say things like this. Prove that A divides C. You can use this definition that I have written to prove it, right?
Mm-hmm.
because B is equal to AK and C is equal to BM something. K and M are integers.
Yes, sir.
So from there it will come that A divides C. So that is the transitive property. The third property is if A divides B and B is not equal to 0, then mod of A is less than equal to mod of B. So whenever A divides B, mod of A will always be less than equal to mod of B, right? The equality case is obvious when both the numbers are same, A is equal to B, right?
Mm.
And this is a special case where B is not equal to 0 because any integer always divides 0. Any integer A will always divide 0, right? So
Yes, sir.
that is an exception. We will not say mod of A is less than equal to mod of 0 because in that case, that doesn't work, right? So except for B equal to 0, all other cases this will be true because B is a multiple of A. Modulus of B will be more than modulus of A, right?
Yes, sir.
I hope this is clear. This is an important property because we'll be using it to prove equality. In number theory, when we try to do proofs of things, many times we have very little information. And suppose you had to prove like mod A is less than B or something, right? One way to prove it would be to prove that A divides B because that will imply mod of A is less than equal to mod of B, right?
Yes, sir.
Yeah.
At least that will get you close to it, right?
Yeah.
Close to
Mm.
the proof. Similarly, if A is greater than B, you would try to prove the opposite,
That B divides A.
right? And one way to prove equality, if A is equal to B, you have to prove, then one way to prove it would be prove that A divides B and B divides A.
Then A can be plus minus B, right?
Yes. Anytime when you do divisibility, the integers can be plus or minus. Because divisibility depends on this relation. A divides B means B is equal to AK. K can be any integer, positive or negative. So when I say factors of 5, factors of 5 are not just 1 and 5. You can also say minus 1 and minus 5. Like negative numbers are also factors. So you don't have to, especially in divisibility, you have to be careful. It could be negative. So, but usually when we count factors, we don't care about the negative factors. So that is a bad example. But in divisibility, we definitely ensure that K can be any integer. It could be positive or negative. So what I was saying was, if you wanted to prove that A is equal to B, one of the methods is to prove that A divides B and B divides A. Because that will mean that mod A is less than equal to mod B and mod B is less than equal to mod A, which will only happen if both the mods are equal.
Yes, sir.
So the reason this property is being mentioned, it may seem like an obvious thing. The reason it is being mentioned is because it will be used later in proofs, where it will be not at all obvious how to prove something. So if it is seeming like very trivial, you just have to wait for a few more sessions and you will realize that it is not trivial at all. So don't worry about it if it seems very obvious. It will not be obvious soon. The fourth property is this: if A divides B and A divides C, then this is very important. Then A divides alpha times B plus beta times C for any integers alpha beta. Basically, we are saying that A will also divide a linear combination of B and C, right?
Yes.
This is like a linear combination of B and C. We already know that A divides B and A divides C.
Hmm.
So it will divide a combination of B and C with any integers. Doesn't matter what integers we put.
क्योंकि A will come out as common.
Right.
Hmm.
Because you will say B is equal to A K1 and C is equal to A K2.
And it is multiplied. So A K1 alpha plus K2 beta.
Right. So
Hmm.
from there you can prove that this will always be true.
Hmm.
Yes, sir.
This type of result will be useful again in proving divisibility because sometimes some integers can be expressed as a linear combination of others. For
Okay.
example, you might have seen, if you have seen IMO 1959, the first IMO, there is a problem on
Irreducible
divisibility.
one.
Huh?
The irreducible one.
No, there is a problem on divisibility, some 21n plus something something by this. A question hai, which is based on this principle only, divisibility.
Yes, sir.
It is very similar to this, like it just depends on this direct question.
Hmm.
So if you know this property, then you can do that problem. Anyway, you will be seeing applications of this soon. Then the last property is if A divides B and A divides B plus minus C, then A divides C. It's a converse type of relation from here, right? So basically, it's like
Yeah.
saying A divides B and A divides a combination of B and C, then it will divide C. It's like almost like a converse of this, right?
Yes, sir.
So again, the proof is obvious here. There is no issue with the proof. Correct?
Hmm.
These proofs you can finish yourself also. There is no problem here. So I'll move on.
Yes, sir. Yes.
One of the corollaries is, which I already mentioned, I will say again, if A and B are integers and A divides B and B divides A, then mod of A is equal to mod of B, and we can say A is equal to plus minus B.
Sir, what is the definition? What do you mean by corollary? Is it something other than theorem?
It is a consequence of our result earlier.
Acha, okay.
It's something that follows from the statement we made earlier. A divides B, then mod of A is less than equal to mod of B. This is coming from there only, right? Corollary means anything that follows from some previous statement. So
Yes.
this is, we have already discussed. So now what I will let you try to figure out is this problem. Let n be an integer. Prove that the only common divisors of 2n plus 1 and 3n plus 1 are 1 and minus 1. And B, what common divisors can 2n plus 1 and 7n plus 1 have? So use what we have discussed so far to try to figure this out.
Sir, first one done.
Yes, sir. You have to explain कैसे हुआ है.
Sir, we will let assume like if A divides 2n plus 1 and if like something A divides 3n plus 1, then we will use the theorem like if A divides B and A divides C, then A divides A alpha B plus beta C.
Mhm.
And we can use like if a divides 2n plus 1 and if a divides 3n plus 1, then a divides 3 times 2n plus 1 minus 2 times 3n plus 1. So from here we can get like a divides 1. So therefore a can be plus minus 1.
Right. So we are saying that any common divisor of this and this will also divide a combination of these two, right? So if A is a common divisor of this and this, it will also divide 3 times this plus minus 2 times this. But that actually turns out to be 1. So that means A divides 1, and that automatically means A can be only plus or minus 1. So
Yes,
that
sir.
is the type of thing that happened in that IMO problem also.
Hmm.
IMO 1959 problem was also like this only. Same thing you should try here also.
Is it like 1 and 5?
You should say 1 minus 1, 5 minus 5.
1 minus
Yes,
1,
sir.
5 minus 5, yeah.
If you combine them with 7 and minus 2,
Hmm.
minus 2,
Minus 2, 7 and plus 1. Yeah, it's like,
you're getting 5. So you're saying any common divisor of this will also be a divisor of 5, right?
Yes, sir.
A divides 5, which means A can be 5 is a prime number, so only 1 and 5. So it can
5
be plus minus 1, plus minus 5.
plus minus 5. Yes, sir.
So that is pretty obvious, and we are using property 4 that combinations, linear combinations are also divisible by the divisors, right?
Yes, sir.
Yes, sir.
Another question is find all integers n for which n square plus n plus 1 divides 2n square plus 1. You should try this question. It might take a little more time than what we have left. Also, there are many like videos on the channel which are based on divisibility problems. There are like at least 4 or 5 videos that I have made on divisibility. You should check out all of those videos for the questions that are explained there and practice these divisibility problems. These are the basic steps that you have to take when you start number theory. So you need to be quite confident handling these. You should also know your basic maths like criteria of divisibility for all the different numbers. At least you should know your basic numbers. What are the criteria for divisibility? So go through my channel, go through the number theory videos. Last couple of months, there have been several videos I have posted on divisibility. You should look through them and try the problems there. What we will do in the next class is discuss the solution to this problem, and then we'll start with a discussion of start with congruences, because congruences help us finish divisibility problems easily.
Yes, sir.
So we'll discuss congruences starting from next class. So try this problem, go through the channel for other divisibility videos, and use the references that I said at the beginning of the class to learn more. And we'll continue from this point in the next class. Is there any question anybody has?
No, sir.
No, sir.
No.
Okay, fine. That's all for now then.
Thank you, sir.
Okay, sir. Thank you.